Let's begin then by remembering that we're looking at a reaction in the Haber process between nitrogen, hydrogen forming ammonia, and analyze what happens when we change pressure, temperature, concentration, or whatever else. And this introduces a profoundly important concept, and it's a concept of the reaction quotient. And the reaction quotient is designated Q, and that reaction quotient carries with it exactly the same functional form as the law of mass action that drove the functional form of the equilibrium constant. So we're going to write this in terms of the pressure of the product, NH3 squared, divided by the pressure of N2 times the pressure of H2 cubed. But the important thing about the reaction quotient is that I can write it for any position from all reactants all the way through to all products. That is, I can write the value of Q for the full range of species concentrations, whereas I write the equilibrium constant, in this case at constant pressure, for the unique position of equilibrium where delta G is equal to 0. But by expressing the reaction quotient, it means I can analyze the relationship between the position along that reaction coordinate from reactants to products at any point by writing down the value of Q. So let's assume we've reached equilibrium. And so let's write the reaction quotient Q, and that, of course, has the same functional form as what we have just sketched out. It's the square of the pressure of ammonia divided by the pressure of N2, pressure of H2 cubed. But if we've reached equilibrium, then Q is equal to the equilibrium constant expressed in pressure units. However, let's suppose that we stress the system, and by the word stress, I mean if we increase the pressure on the system, decreasing its volume, or change concentrations, or change temperature, that's a stress on the system because it's driving it from its comfortable position of equilibrium. So let's suppose that we have compressed this mix by a factor of 2, and we can write Q after the stress has been applied as the pressure of NH3 after, and I need to divide that by the pressure of ammonia before, that's at equilibrium, and I have to square that. Then I have to divide all of that through, and I can shorten that up a little bit by writing the pressure of N2 after divided by the pressure of N2 before, and I want to take that to the stoichiometric coefficient, but that's just 1. And for my other reagent, I have the pressure of H2 after divided by the pressure of H2 before, and I have to raise that to the stoichiometric coefficient, or cube it. Well, the ratios are easy because I have compressed that system, decreasing the volume to half of its original, and that means I've doubled the pressure in each case. So that means that the pressure after divided by the pressure before for ammonia is 2, and I have to square that. And for the case of nitrogen, the ratio is 2, but that's raised to the first power, and then I have a factor of 2 cubed for my ratio before and after for hydrogen raised to its stoichiometric coefficient. And when I calculate that out, that gives me 1/4. But that's extremely important because now I have the reaction quotient after. That's simply equal to 1/4 of the reaction quotient before. But because I was at equilibrium, Q before is the equilibrium constant, so that's 1/4 of the equilibrium constant in pressure units. Well, that tells me something very profound. That means that if I come back to my surface of Gibbs free energy for the reactants, Gibbs free energy for the products, and I analyze the fact that when I reach that equilibrium point, delta G equals 0, I know I was sitting right here at equilibrium. Well, if I've increased the pressure and now the new position defined by the reaction quotient is less than the equilibrium constant, that means I'm sitting over here somewhere and I have a condition where Q is less than the equilibrium constant, again expressed in pressure units. Well, we know exactly what will happen now. Equilibrium chemistry comes into play. I'm sitting on a slope that slopes downward. Delta G is less than 0, so I'm going to move spontaneously in the direction of producing more product. And I move down that curve until I hit the magic point where delta G equals 0 again, and I'm back in equilibrium. But this analysis tells us exactly what the dynamic of this is going to be. If I increase the pressure by a factor of 2 and I put that new expression into the reaction quotient, that tells me the relationship between Q just following the stress and the equilibrium constant before I applied that stress. And I can do the calculation. In this case, I'm shifting to the right to find the new equilibrium position, but in many other cases I can have the reverse true, and that is that Q is greater than the equilibrium constant pressure. And the minute that's true, I know that my free energy is going to drive me back toward the equilibrium condition. So this is a major accomplishment, because now not only do we understand equilibrium chemistry, we understand equilibrium chemistry when we apply a stress to that. So we had our good old reaction of N2 plus hydrogen going to ammonia as an example of our favorite reaction, A plus B going to C plus D. And we established the fact that anytime the applied stress creates a situation where the reaction quotient is less than the equilibrium constant, that puts us in this position immediately following the stress, and the equilibrium chemistry drives us back toward the equilibrium point. And so that means we're shifting from the left to the right when Q following the stress is less than the equilibrium constant. It's just equally true if we now stress the system and we end up with the reaction quotient being greater than the equilibrium constant, then the equilibrium chemistry drives us directly back to the equilibrium point where delta G is equal to 0, and that means that we shift from the right to the left under those conditions. And this is an application that immediately tells us how the response of an equilibrium will relate to an implied stress. And now we're going to look at a couple of examples of different types of stress.